In the summer of 2013, deep inside a set of man-made caves on the shore of the Red Sea, a team of French archaeologists uncovered something that would rewrite everything we thought we knew about how the pyramids were built. It wasn't gold, it wasn't a hidden chamber, it was papyrus. Torn, faded, and over 4,500 years old, these fragile sheets turned out to be the oldest inscribed papyri ever found in Egypt. And they weren't myths or religious texts, they were a workman's. For centuries, this was the greatest unsolved engineering mystery on Earth. How did a civilization without iron tools, without the wheel in any practical form for heavy hauling, without pulleys, as we understand them today, manage to quarry, transport, and stack over 6 million tons of stone into a structure so most scholars place at around 20 years. That works out to roughly one large stone block being set into place every few minutes of every working day, for 2 decades straight. No slipshod guesswork could produce that. It required a level of logistics, mathematics, and labor organization that would not be out of place in a modern infrastructure project. The old popular image of enslaved masses whipped into hauling stone under a merciless sun has been steadily dismantled by archaeology over the past 3 decades. The turning point came from the ground itself, at a site just south of the Sphinx, where archaeologist Mark Lanner and his team from Ancient Egypt Research Associates began excavating what is now called the lost city of the pyramid builders. What they found was not a slave camp. It was a planned town with bakeries capable of producing thousands of loaves of bread a day, breweries producing beer by the vat, and butcher yards where evidence shows workers were fed cattle, sheep, and goat on a scale suggesting organized, state-supported rationing rather than punishment. Skeletal remains recovered from a nearby cemetery show healed fractures that had been set and treated, meaning injured workers received medical care rather than being discarded. These were not disposable slaves. They were a rotating labor force, likely drawn through a system of national conscription, organized into gangs with names like Friends of Khufu and Drunkards of Menkaure, names painted directly onto blocks that survive to this day. Merer's diary confirmed this from the other direction. It reads like a modern spreadsheet, tracking bread, beer, grain, and meat delivered to work crews, and recording exactly what was owed and what had been paid. The men who built the pyramids were fed, housed, and compensated. Understanding who built the pyramids turned out to be the first step in understanding how. This level of bureaucratic record-keeping tells us something crucial about pyramid construction. It wasn't organized chaos powered by brute force. It was a state-run logistics operation with inspectors, quotas, deadlines, and paperwork, closer in spirit to a modern government construction contract than to any popular image of ancient slave labor. The stone itself came from multiple, carefully chosen sources, each selected for a specific purpose based on the properties of the rock. The core of the pyramid, the vast bulk of its volume, was built from local limestone quarried directly on the Giza Plateau itself, Kure. His diary describes loading limestone blocks onto wooden boats at Tura and sailing them up a network of canals to a basin near the pyramid itself, a harbor essentially built to receive the stone at the construction site's The granite itself deserves its own explanation, because quarrying it required an entirely different technique from the softer limestone. At Aswan, where the Egyptians extracted granite for over 3,000 years, the clearest surviving evidence comes from the unfinished obelisk, a single-piece monument that cracked during extraction and for modern archaeologists to study. Workers first marked the outline of the block using string lines coated in red ochre, then cut narrow trenches, some only around 60 to 75 centimeters wide, just enough room for a worker to crouch and swing a tool around the entire perimeter of the stone. Rather than cutting the granite the way a chisel cuts wood, workers pounded it into submission using dolerite, a volcanic rock even harder than granite itself, shaped into fist-sized rounded hammerstones. Researchers who have studied thousands of these pounders found at Aswan estimate their average diameter at around 14 centimeters, and experimental archaeology conducted directly at the site in recent years. Deep enough to isolate the block from the surrounding bedrock, workers drove wooden wedges into cut slots and soaked them with water, and as the wood absorbed moisture and expanded, it generated enough force to fracture the granite along the intended D line. This same granite, quarried in this labor-intensive, physically punishing way, was then floated more than 800 kilometers down the Nile to Giza for use in the pyramid's most structurally critical chambers. This water transport system is one of the most important pieces of the puzzle that archaeology has only recently confirmed with hard physical evidence. For years, the idea that boats could get anywhere near the Giza Plateau seemed implausible, since today the Nile flows several kilometers away from Tiwanaku pyramids. But a 2024 study published in the Journal of Archaeological Science, led by geoarchaeologist Haider Shesha and colleagues, used sediment cores drilled around the Giza Plateau to reconstruct the ancient landscape. The results confirmed that during the Old Kingdom, a now-vanished branch of the Nile, referred to as the Khufu branch, flowed much closer to the pyramids, and that water levels during this period were unusually high, making the region far more navigable than it is today. Combined with Merer's account of a harbor called the Lake of Khufu, the physical geology and the written record now align. The ancient Egyptians did not haul 6 million tons of stone entirely by muscle across open desert. They engineered a river transport network, digging canals and basins to bring the stone as close to the building site as the landscape would physically allow, then relying on human and animal power only for the final, shortest stretch. Once the stone reached the plateau, the challenge became lifting it, sometimes hundreds of feet into the air, with nothing but wood, rope, copper tools, and human effort. This is where the debate among Egyptologists has been most active, and where recent discoveries have narrowed the possibilities considerably. The dominant, best-supported theory involves ramps, but not a single, simple ramp, running straight up one face of the pyramid, an idea long ago dismissed because such a ramp would eventually need to be longer than the pyramid is tall and would require more material than the pyramid itself. Instead, the evidence increasingly points to systems of ramps that wrapped around the structure or spiraled up its face as it grew, adjusted and rebuilt continually as construction progressed. Direct physical proof of an actual working ramp system came in 2018, when a joint mission from the French Institute for Oriental Archaeology and the University of Liverpool, led by Yanis Gordon and Roland Enmarch, excavated an ancient alabaster quarry at Hatnub in Egypt's eastern desert. What they found was remarkably well preserved. A central ramp, flanked on both sides by staircases lined with regularly spaced post holes, some large enough to have held wooden posts nearly half a meter thick. Inscriptions at the site date the ramp to the reign of Khufu himself, the same pharaoh who built the Great Pyramid. The design suggests a genuinely clever solution to a problem that had puzzled engineers for years: how to move heavy loads up dangerously steep slopes without the whole system sliding backward. Workers would load a stone block onto a wooden sled, then use ropes threaded around the wooden posts as anchor points, essentially functioning as primitive pulleys, allowing one team to haul from above, while another controlled the descent from below, distributing the load and preventing catastrophic slippage on a ramp with a slope steeper than 20%. Far steeper than earlier models assumed was possible. This was a system built for extreme desert quarry work, and while archaeologists are careful not to claim it was the exact method used at Giza, it demonstrates conclusively that 4th Dynasty Egyptians, in Khufu's own era, possessed the engineering knowledge to build ramp and lever systems capable of moving multi-ton blocks up steep inclines, using wood, rope, and coordinated human labor alone. The physics of actually dragging these blocks across flat ground before they ever reached a ramp is itself well understood, thanks to both ancient artwork and modern experimentation. A famous tomb relief from Deir el-Bersha, depicting the transport of a colossal statue of the nobleman Jehudiotep during the Middle Kingdom, shows dozens of men hauling a sledge while a single figure stands at the front, pouring liquid onto the sand just ahead of the runners. For a long time, this was assumed to be a ceremonial or ritual act, but physicists studying granular friction have since demonstrated that wetting sand to just the right degree, not too dry, not waterlogged, can dramatically reduce the friction between a wooden sledge and the ground, because the water creates capillary bridges between sand grains that stiffen the surface and prevent the sledge from digging a trench in front of itself as it moves. Experiments replicating this technique found that the correct application of water could cut the required pulling force by as much as half. Applied to the pyramids, this means gangs of Egyptian workers were not just brute forcing multi-ton blocks across the desert. They were applying a real, empirically effective material science technique, hundreds of years before anyone could have explained why it worked in scientific terms, purely through observation and repeated trial. Recent computational modeling has added further weight to the ramp hypothesis, while refining exactly how it might have scaled up to the size of the Great Pyramid. A detailed simulation published in late 2025 modeled what researchers call an edge-integrated multi-ramp construction system, essentially a network of ramps built directly into the pyramid's edges and corners, rather than one long external incline. This model accounts for the traffic flow problem archaeologists had long worried about, because with thousands of workers moving blocks simultaneously, a single ramp would create the ancient equivalent of gridlock. A multi-ramp system, allowing different work gangs to move stone up different faces of the pyramid simultaneously, solves this bottleneck and matches the pace of construction implied by the timeline of roughly 20 years. The researchers behind this framework borrowed modeling techniques from modern traffic engineering, treating each ramp segment as a channel with a maximum throughput, and found that a network of edge ramps growing in height, alongside the pyramid itself and periodically dismantled and rebuilt as each new tier was completed, could plausibly deliver enough stone to match the construction pace implied by both the mirror diary and the physical volume of the finished monument. This doesn't mean the debate is entirely settled. Some Egyptologists still favor a single large frontal ramp for the lower courses of the pyramid, transitioning to smaller wraparound ramps higher up, where a straight incline would have become impractical. What nearly all serious researchers now agree on, regardless of which specific ramp configuration they favor, is that some form of ramp, lever, and sledge system, built, modified, and rebuilt in stages as the pyramid rose, remains by far the best supported explanation, consistent with every piece of physical evidence recovered so far, and requiring no technology beyond what 4th Dynasty Egypt is independently known to have possessed. Not every proposed solution is held up to scrutiny, and it's worth being honest about the ones that remain speculative rather than established. In 2025, a French research team led by engineer Xavier Landreau published a hypothesis in the journal PLOS One, proposing that the Egyptians used a hydraulic lifting system, essentially a kind of internal water-powered elevator, to raise stones vertically through the pyramid's core using specially designed shafts. The theory builds on the team's separate and more solidly supported discovery concerning Gizr el-Mudir, a massive enclosure near the step pyramid at Saqqara, whose true function had puzzled archaeologists for over a century. Landreau's team argued, based on satellite imagery, ground-penetrating techniques, and hydrological modeling, that Gizr el-Mudir functioned as a check dam, designed to capture and control seasonal floodwater and sediment before it reached a nearby dry valley, effectively an ancient water management system. This part of the research, that Old Kingdom Egyptians engineered structures to control floodwater near construction sites, is compelling and consistent with what we already know about Egyptian irrigation skill. But the leap to an internal hydraulic elevator lifting stones inside the Great Pyramid itself remains a minority hypothesis, unproven by physical evidence inside the pyramid, and it has drawn skepticism from many Egyptologists who point out there is no confirmed archaeological trace of such an internal shaft system, and that the ramp evidence from sites like Hatnub already accounts for the observed construction pace without requiring it. Responsible science means presenting this as an intriguing but unconfirmed idea, not an established fact. While the big structural questions were being worked out with ramps, sleds, and ropes, the finer craftsmanship depended on tools that were remarkably advanced for their time, despite predating iron by well over 1,000 years. Egyptian workers cut and dressed limestone using copper chisels and saws, copper being a soft metal by modern standards, but effective against limestone, especially when the copper was work-hardened. For denser stones like granite, they turned to even harder materials. Dolerite pounding stones, essentially fist-sized balls of an extremely hard volcanic rock, used to literally pound and abrade granite into shape through repeated grinding impact, a slow but astonishingly effective technique, since dolerite is harder than granite itself. Archaeologists working at the Giza site continue to recover physical examples of these tools. As recently as 2025, researchers cataloging artifacts from Leonard's Lost City excavation described a copper chisel tip, worn and reshaped from heavy use, direct physical evidence of the tools that shaped stone for one of the most technically demanding buildings on the planet. Sandstone and other quarries, like those at Gebel el Silsila, further south along the Nile, show similar tool marks and quarrying techniques, providing a broader picture of how the ancient Egyptians organized stone extraction as a coordinated empire-wide industry rather than a single isolated project. None of this happened in an environmental vacuum, and recent paleoclimate research has helped explain why the Egyptian state was even capable of mustering this kind of labor and resources in the first place. Studies of ancient plant remains and sediment records from the Giza area, published through the Ancient Egypt Research Associates project, show that the climate during Khufu's reign was significantly wetter than it is today, with more reliable Nile flooding, supporting the reliable grain surpluses needed to feed a large, non-farming labor force for months at a time. Agricultural surplus is easy to overlook in a story about stone and ramps, but it was the actual foundation the entire project rested on. Without predictable floods, generating enough grain to feed tens of thousands of quarrymen, boat crews, bakers, and stonemasons, through the several months each year when farming activity slowed and labor could be redirected toward the pyramid, none of the engineering described so far could have been sustained the same. Research also indicates this favorable climate window began deteriorating in the centuries following the Pyramid Age, a shift some scholars connect to the eventual political fragmentation of the Old Kingdom, underscoring just how tightly Egyptian monumental construction was bound to the rhythms of the Nile. The precision of the finished structure is where all of this technology and organization comes together most visibly, and it remains genuinely astonishing by any standard, ancient or modern. The Great Pyramid's four sides are oriented to true north, with an average error of only about 3/60ths of a degree, a level of accuracy the Egyptians most likely achieved using astronomical observation, tracking the rising and setting positions of specific stars to bisect the angle and determine true north without a magnetic compass, which did not yet exist. The base of the pyramid, despite being carved from bedrock that itself was leveled with extraordinary care, shows almost no deviation across its entire footprint, likely achieved using water-filled trenches as a leveling tool, since water naturally finds a perfectly horizontal surface, combined with careful surveying using sighting rods and cord. Egyptian surveyors also relied on simple but effective tools like the merket, a plumb line combined with a horizontal sighting bar, used in pairs to establish true north by tracking a chosen star as it crossed the meridian on two separate nights, then bisecting the angle between the two sightings. None of this required advanced mathematics by modern standards, but it demanded patience, repetition, and an institutional culture that valued precision enough to check and recheck its work across a project spanning 2 decades and multiple generations of surveyors, since the men who began laying out the pyramid's foundation were not necessarily the same men alive to see it completed. Every one of these individual techniques, quarrying, water transport, ramp construction, sledge lubrication, and astronomical surveying, had to function together, continuously without major failure, for the better part of 2 decades. A single serious miscalculation in the base leveling would have thrown off the entire structure as it rose. A failure in the grain supply chain feeding the workers' town could have halted construction for a season. A collapse of a ramp under load could have set the project back by months. That none of these failures derailed the project. That the pyramid rose essentially on schedule and remains standing and structurally sound 45 centuries later is itself a form of evidence. It tells us the ancient Egyptian state had built something we don't always give it credit for. Not just a monument, but a functioning bureaucracy capable of long-term planning, resource forecasting, quality control, and the coordination of tens of thousands of specialized workers across quarries, waterways, bakeries, and a construction site, all pointed at a single generational goal. Modern non-invasive scanning technology has also opened an entirely new chapter in pyramid research, one focused less on how the structure was built and more on what still lies hidden within it. The Scan Pyramids Project, an international collaboration using cosmic ray muon imaging, a technique that essentially takes an X-ray of a massive structure using naturally occurring particles from space, discovered a previously unknown corridor near the pyramid's north face in 2023, later explored using a specially designed microendoscopic camera. Then, in 2025, a separate research team applying electrical resistivity tomography, a technique that maps subsurface structures by measuring how they conduct electricity, detected air-filled anomalies behind the eastern face of the nearby pyramid of Menkore, possibly indicating a second, previously unrecognized entrance. Researchers are careful to stress that the full extent and purpose of these anomalies remain unconfirmed, and her investigation using muon imaging and endoscopic cameras is ongoing. These discoveries don't fundamentally change our understanding of how the pyramids were built, but they demonstrate something important. Even after more than 2 centuries of formal Egyptological study, and after 4.5 millennia, the Giza Plateau has not finished revealing its secrets. Every one of these scanning technologies is explicitly non-invasive, a deliberate choice by the archaeological teams involved, since the goal is to understand the interior of monuments this significant without drilling into them or risking structural damage, a very different ethic from the more destructive excavation methods used by explorers a century and a half ago. What emerges from all of this evidence, the workers' town with its bakeries and medical care, the diary of a boat captain who transported limestone up a long-vanished branch of the Nile, the rock-cut ramp at Hatnub with its ingenious system of posts and ropes, the copper chisels and dolerite hammers, and the astronomical precision of the finished monument, is not a story of mystery or ancient secrets beyond human comprehension. It's the opposite. It's a story of a civilization that mastered mathematics, hydrology, astronomy, metallurgy, nutrition science, and large-scale project management, all 4,500 years before the invention of the wheel and axle systems and iron tools that later civilizations would take for granted. No lost technology was needed. No outside intervention was required. What built the pyramids was human intelligence, applied with extraordinary patience and extraordinary discipline by tens of thousands of ordinary people organized into something extraordinary. Every generation since. S looked at the Great Pyramid and wondered whether its builders had access to some secret since lost to history, some forgotten machine, or vanished science. The genuine archaeological record tells a different, and in many ways, more impressive story. The secret was never a lost technology. It was disciplined observation, applied consistently at a scale few societies before or since have ever attempted, using nothing more exotic than stone, copper, wood, rope, water, and the coordinated effort of an entire nation. The Great Pyramid remains the only one of the 7 wonders of the ancient world still standing, not because its builders had access to a secret we've lost, but because they understood stone, water, rope, and each other better than almost any civilization before or since, and because they built it to last. If you found this as fascinating as I did piecing it together, do me a favor and hit that subscribe button, because we're going to keep digging into the real science behind history's greatest mysteries. No myths, no aliens, just the evidence. Drop a comment below and tell me which ancient engineering feat you want us to break down next. Give this video a thumbs up if you learned something new today, and I'll see you in the next one.